So just in case tomorrow there is a quiz, you can check the announcement. And for the recitation, and I will move around some of the deadlines. I always keep forgetting to move the correct deadlines for the assignments, but don't worry, like the online assignments. I mean, like so. If there's some deadlines that were recent, like I'll change those. Um, so don't worry about that. So the plan for today is just to continue talking about this power series stuff. Let me see. Oh, I have to connect. I have to plug it in. Okay, so let's see if I can. What I was saying last time on Monday is that if you have a function, the first derivative approximates that function with a line, then you can use the second derivative to create a polynomial of degree 2 that approximates the function with a parabola, and you can kind of like keep going. So that is like the idea of like the Taylor polynomials. So just to kind of like explain this a bit better now. So let's just talk about the Taylor polynomials. Of so the idea is like you have a function f of x function that you want to approximate. So you want to approximate that polynomial, sorry, that function with a polynomial of a certain degree, because polynomials must have a degree. So let's say that the approximation will have degree n. Okay. And kind of what we were doing last time, I kind of like did it by trial and error with the exponential function to give you like an idea of how that would look like. But in general, like, there was nothing really special about the exponential. It works the exact same way. So the idea is that the polynomial of degree n that approximates that function is the following. So and I'll kind of like first write like the formula, and then I'll write like the first few terms so that you see like how it's structured. So so the formula for the degree n Taylor polynomial is this one. I'll explain the notation in a moment. So this is what is this in practice? This would be f of 0 plus f prime of 0 times x plus the second derivative of 0 divided by 2 times x squared plus the third derivative evaluated at 0 divided by 3 factorial. Let's like I'll put them with factorials actually to make it more clear, times x cubed. And this would go on and on and on until degree n. So the thing is, like, after a while, it is a bit inconvenient to write prime for like more derivatives. After 3, like usually you don't keep writing the prime notation. So that's where like this notation comes in. So whenever you write something like this, like and again, I'm about to say what that means, but here like fk of a function means like the kth derivative. So you put like a parenthesis around the number so that it's not confused with like taking the power k of the function. So So this is called like the kth derivative of the function. Which you would also write if you like the Leibniz notation, although I will stay away from it. How it would be something like this. So it's kind of like saying that k, like to take k derivative. That's what it means. But yeah, usually the way you will see this written down on the textbooks and stuff like that is with this other one. Oh yeah. Oh, I'm about to write the formula in general, like if you had not chosen zero, it's just like right. It's kind of like zero is like a special number in a sense, so it's kind of like good to have like the formula for zero separate from the rest. But yeah, like there's almost no difference. Like that's what I'll do next. Basically you replace zero with a here, and then x with x minus a, and that's all. Like if you wanted to use another point, so there's almost no difference, but it's still useful to because m- many things just simplify if you can put x equals zero somewhere, so like it just makes a but yeah, I'll give like a in a second like the formula if you had chosen like another point that's not zero, if that makes sense. Oh sorry, yeah, did I see it? Well, it's not a power series until we take n goes to infinity. For now it is called like a Taylor polynomial of degree n. Yeah, the goal kind of like we'll start talking about this today. Like kind of like the idea behind is like you should think of this as a better approximation to the actual function, at least near in this case near zero, because that's where like you're kind of like using that as a reference point. And in a sense, what you would like is that it becomes like a perfect approximation at infinity. Well, and a perfect approximation is just like the same as saying that they're equal. So what you would like to say is that as n goes to infinity, that literally gives you back the function. And that is true kind of like for the functions you have studied so far, like like mathematically, you can always come up with monsters where like things always fail, but like for like the majority, and we'll talk about this a lot, like for like the next few days, for next few classes, for the majority of functions that this is basically correct. Like you can always approximate the function. It can be written as a limit of polynomials, and that's kind of nice because polynomials are very easy to work with. There are other things like, and this is not something we do here, but I'll maybe show you like an animation one day. Like you can also approximate a function with sines and cosines. I may have mentioned that, and that's what the Fourier series is all about. That is more useful when like the function is periodic, because like sines and cosines are periodic functions, so you can approximate, you know, that's another way to approximate it. So I'm not saying that this is like the only way to approximate a function, but it's like certainly the most natural way if you just think about it from the perspective of a derivative. You start with lines, you start with parabolas, then you move to cubics, then quartics, quintics, blah, 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 and then you go forever. Yeah, but what I was trying to say before moving on to the formula in the general case is that what's nice about this polynomial is that it coincides with the function at zero. Like the value of the function is the same as the value of the polynomial. The first derivatives are the same. The second derivatives are the same up to the nth derivative. It's designed so that it works that way. So what the nice property of this polynomial of Pn is that the value at zero is the same value as the function at zero. The first derivative at the origin is the same as the first derivative of the function at the origin. The second derivative is the same as, like they do agree, like it is constructed so that it agrees with like the first derivative, the second derivative, the third derivative, up to the nth derivative, they all agree at zero. Like, at different places it would be different, but at least at the value 0, they would go agree. So it agrees with the function up at 0 up to derivative xn. Very. Oops, sorry, let me just. Before giving like the general formula, let's do another approximation. So let's take something that we know a lot very well, like cosine. So let's say I wanted to approximate cosine of x by a polynomial of degree 4. That's not too bad, and we can do it like but this is a good example to kind of like get a feeling for how the approximations look like. So here's an example. Find the degree 4 Taylor polynomial for the cosine of x. Does this look a little bit better or what? It is better, right? Like this. I don't want to turn it off completely, but I just want just like right. Let's leave it like that, but it doesn't have to go. So if you want a degree 4 polynomial, what that means is that you need the first 4 derivatives because it goes up to degree 4. So you need to find, like the function is already a given, that will always be given. So you need to find the first 4. So you can make it as a table. That's kind of convenient. Okay. So this is kind of going to be like so you need the function and the value at the origin, because here we're using 0 as a reference. Okay. Oops, sorry about that. So at 0. So the function is cosine of x. The first derivative, as you remember, is minus sine of x. Then the second derivative is negative cosine of x. I should have, let me see if I can, let me write this a little bit bigger because it doesn't look that great. Minus sine of x. Then the second derivative is negative cosine of x, right? Then the third derivative is, so the derivative of cosine is minus sine because of this minus sign. So you get sine of x. And the fourth derivative, which again, it already starts looking ugly if you put prime, 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 prime. So I'll just put like the 4 just to emphasize that that's the same. That is cosine now. Yes.
So if the problem is find the degree blank Taylor polynomial, you assume the reference is 0?
Yes, and if not, I would say add x at another number, at the number 3 or 4 or whatever. Yeah. but like the standard reference will always be 0 for us. Because as you see, like it doesn't, like now we have to evaluate this, and it's just like a lot, like, for a cosine or a sine, it's usually easier to evaluate at 0, pi over 2, places where you do know actually the values. So if I had said like x equals 1, what is cosine of 1? It's like that,
Yeah.
and what, nothing, like, like you don't really know it. So, but yeah, like, unless stated separately, like the reference point will always be x equals 0, because that just makes, for most things, like that's just so much faster to evaluate, you see. That makes sense. Okay, so let's just plug everything here at 0. So what is cosine of 0? Cosine of 0 is 1, right? What is, well, minus sine of 0? Sine of 0 is 0, right? So I'll just put, sorry, oh my God, like this is terrible. So like this is 1, then sine of 0. You have to be careful when evaluate it, believe it or not, because there's so many evaluations you have to do. So now cosine of 0 is 1, but now there's a minus sign, right? And then sine of 0 is again 0. And then cosine of 0 is 1 again. Then so my recommendation is always just find always all the derivatives that you need, and then do the plugins. Like, so evaluate them to the very end. That makes it a bit easier. And so according to the formula, I'll write it kind of like in general, and then I'll just plug in the corresponding numbers to kind of like identify what it's saying. So like the formula says it would be f of 0 plus the first derivative at 0 times x plus the second derivative at 0 times 2 divided by 2 factorial times x squared plus the third derivative at 0 divided by 3 factorial times x cubed, right? Plus the fourth derivative at 0 divided by 4 factorial times x to the 4. Okay, so that's like the degree 4 approximation. So let's see how that looks like for this specific number. So I'll erase. This is kind of like what's specific about the cosine, like, like the values of the derivatives. Okay. So let me erase that and replace it with these numbers that we just found. Okay. So f of 0, we said it was 1. Actually, I should have used a different color here. So that is all. And what else? I haven't used purple. Perfect. Okay. So f of 0 is 1. Then you put a 0 times x, right? And you'll see something really cute happens, like, but just wait for a second. Then -1 is the next number, right? Then the next is followed by 0, and then followed by 1 again, right? Is that okay? Is that so good? And there are a few simplifications that do occur, right? Because of these two zeros, right? So you don't really see those terms. So the degree 4 approximation is 1 minus x squared over 2. We skip the cubic term. And then what is 4 factorial? That's 4 times 3 times 2. So it's 12 times 2, which is 24, right? So it should be plus x to the 4 over 24. Okay. And what is nice about this polynomial is that it only has, for example, even powers, right, of x, which is even, right? Like cosine is an even function, so that's not a coincidence, right? Like it's like a, it's because we are exploiting the fact that, like, it's even with respect to, x equals 0, right? Like that's why, for example, x equals 0 is a useful number to use here. So like only even powers appeared in the cosine function, right? But it's not as appreciated until you do a picture. So let's graph it so that you can see how the polynomials look, because that's kind of like the nice thing to observe, right? So let me switch for a second to the computer. Let's go to GeoGebra. So let's go to the calculator. Okay. So let's take our function, which is cosine of x. Perfect. So since this is going to be close to 0, like the idea is like the polynomial, because I'm approximating around 0, like this is where like it should look really good. And then as we zoom out, you'll see like the difference start like to become more evident. But okay, so the first term, I'll just write p of x for polynomial. So if you just put 1, which is the first term that appears, that's what you would call like the degree 0 approximation. So you're just approximating for something that doesn't even depend on x. So that is like a line. But even like a horizontal line, because there's no x dependency. So the line is not tilted. Okay. So that's like the, because then, so this is degree 0, then the next term in the polynomial would have something with x. But there's no x here because it was being multiplied by 0, right? So we can skip that one. Then the next term would be, it was minus x squared over 2, if you remember. Okay, and now this looks a lot better, right? And it does reflect the concavity of the cosine, for example. And you see, like, it does look very close apart. Of course, it fails miserably once you move a little bit later, because, like, it is not supposed to be a good approximation everywhere. Like, you're choosing your favorite point to do the approximation. And then there would be a cubic term in general, which we're skipping because there was a 0 in front. And then what was it? X to the 4 plus 24. Okay. So that's how like now it looks. Okay, so it kind of like now it had to adjust, it wanted to adjust the fact that the concavity is starting to change. So you see like the polynomial does a turn now. And kind of like, again, kind of like what's amazing is that if you kept going this like fifth derivative, sixth derivative, seventh derivative, eighth derivative, blah, 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 you get degree 8, degree 10, degree 20,000, degree 30,000. And if you take a limit as n goes to infinity, it literally, in this case, would become an identity. For the cosine, it would become like a limit of that, which is kind of like crazy if you think about it, because neither of these terms is periodic. None of these terms is periodic, but in the limit, it somehow becomes periodic. It's not obvious. Like the limit of non-periodic stuff can become periodic if n is equal to infinity. So, but I mean, it doesn't take too much to see, like, like definitely it will fail a lot after a while because of like the periodicity of cosine, right? So like this keeps growing because the polynomials always go to infinity or negative infinity depending on the sign of the leading term. So definitely it fails really bad after a while, but it does approximate pretty good for a while. Yes. Yes, but what I'm saying is that for something but like cosine, if you kept adding terms, right? The approximation for cosine in the limit will work for all the points. So like the series, like that you can create with this, like if you had like a term for x to the 8 and term for x to the 10, x12, x14, if you add all those terms together, kind of like the blue graph literally becomes indistinguishable from the green one. There's perfect agreement. It will always fail if you truncate it, which is how you would say this. If you truncate at a particular power, it could be x to 10 trillion. If you put x to 10 trillion, maybe this looks amazing for like up to here, but then it will always fail, because like the polynomial, because like right, because like cosines are always between -1 and 1. That's the crazy thing, right? Cosines always go between -1 and 1, and a polynomial always wants to go to infinity. So you have to keep adding terms to kind of counteract. The polynomial wants to grow forever, right? And you have to keep adding terms to cancel like the growth of the previous terms. Like, so it's kind of like a tug and war thing where like no one, and it also kind of like explains you why the signs are flipping, because they help each other to cancel. Yeah.
Number, obviously, they can only get a person at a time.
Right.
Limit, is it like an approximation, but it's not identical to the function?
For something like cosine, it will be identical to the function. Not every function it will happen like that, but for something like cosine, it will work for any value of x. It will be exactly the same. But in general, like in theory, it wouldn't necessarily be that. But for something like cosine or e to the x, or most of the functions that you do know about, in the limit is an identity. It's kind of like an equality. And it doesn't matter which x you plug in. But yeah, like there will be functions for what that's not true, and there's always some gap in a sense, but not for like the friendly functions from calculus. Like those, which are called analytic. Later, I will give the name. But an analytic function is one for like the limit as n goes to infinity, makes it like the perfect approximation, like basically like not necessarily everywhere, but like for this, like it does. I'm sorry, let me just. What were you going to ask me? Well, so there will be like there is like a convert, like I'm going to start writing some of these things in a bit. And we can do like an example where it becomes more clear. But like a series has a radius, like has a can converge or diverge, right? And we can use like, and I'll do it in a moment, but like there's a ratio, like you can apply the ratio test, which will give you like an interval of convergence. So outside the interval of convergence is where things can go wrong. What happens is for something like cosine, the interval of convergence is infinity. So it converges everywhere. Like that's how you think about it. Like so the series always works. But there are other functions which I'll write in a bit, where like the interval of convergence does not work everywhere. So like and that's like where the difference is. But okay, that making sense. So, but I mean, you already see like the degree for at least, if you only care about certain like small values of x, then this is like a pretty good like approximation. Um, okay, so let me keep writing a few more things. Okay, so next step is just to write a formula for a value that's not zero, just so that you have it. Although in practice, again, like most of the problems, I'll ask them center at zero just because it makes your life easier and it's conceptually not that different. What's like it is literally the same that's going on. It's just like what if you wanted to approximate somewhere else? So if you want to approximate at a point x equals a, so just like as a remark, if you want to approximate around x equals a, the formula for the polynomial becomes and once you write it, I write it, you'll see it's pretty intuitive. That would make sense. So instead of evaluating the derivatives at zero, you evaluate them at a, where a is the number that you care about. That is like reasonable. So you evaluate the derivatives at the point a. And then basically what you did is kind of like shift like it's kind of like taking like the x-axis and you just move it around. So it's kind of like a shift. So you subtract a from x. It's like a translation, kind of like you know, which you don't notice in the case of zero because x minus zero is x. So that's why that is like the only reason why it simplifies a little bit at a zero because there's no like no difference there. So it's like a shift, basically, like a shift or translation. That's how you should think about it. Okay. Yeah, is that okay so far so good? Okay, so as I was saying, like the ultimate goal that we want to do is what happens if we put infinity here? That's where we're headed, right? What if we replace this with infinity? So like that's the main question that we want to understand like next week, because today I still have to say a few more other things. But the goal is how 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 different is f of x from this thing when you put infinity at the top, like a limit kind of thing. So, which this is what you would call like a Taylor series, by the way. So this will be called later like a Taylor series. And the idea is like for most of the friendly functions that like they are essentially the same, but that's what it has to be qualified. I will later say it a bit better. But like you should really think that for most of the functions that that is more or less correct, that you can replace it with this like infinite polynomial. Yeah.
Example.
Well, actually, I would say like in a couple minutes. Yeah, yeah.
Okay.
No. And it's not that they're and you'll see where the non-friendliness comes from. Like, but yeah. I'll because this is kind of like the first example that you would use, but they're not necessarily crazy. I'm making them sound like they're the same things, but they can just become like for example, if a function has like a vertical asymptote,
Oh, yeah.
things like of that sort, that is where like everything gets messed up in general. Like but there are weirder functions, but yeah. But I'll give a few examples like that in a moment. So this will be called like the Taylor series. But this is actually why calculus, this serious stuff is one of the main reasons where like mathematicians became obsessed with giving proofs about everything, because there were many things that you can just do when you have infinity that like if you're not careful, like it just becomes nonsense. So when you work with infinity, you do have to be really, really careful what you're doing. Like for example, like it's what I was mentioning before, like you can if we were approximating cosine by polynomials, none of the polynomials are periodic, right? But the limit in a sense should be periodic because cosine is periodic. So there are things like that certain properties don't carry through, and you can regain properties at infinity, like being periodic or being between -1 and 1, things like that. So there are many properties that like the pieces can have, but the totality at infinity does not have, or vice versa. So you have to be really careful, and uh, so like that's why a lot of efforts were spent like trying to make everything with a proof and things like that, because that's not how like Newton and Leibniz were like proof things where like they were developing calculus. But like once you get to these type of things, like you do get into many issues if you're not being careful. And then this is like this is very useful thing. Like if you ever have to solve like a differential equation, most like what you call calc for here. Many times you solve it by assuming like that the solution has like a power series, which is how this is going to be called, and you solve like a power series instead. Or if you want, so like there are many reasons why like this approximation like is super important to understand really well. There's this famous heat equation, for example, which tells you how heat propagates, which is, by the way, the same equation that like in financial markets is used to trade stocks and all this stuff. Like it's called the Black-Scholes equation in like and when you're trading derivatives and all this stuff. And like Fourier like has studied it by assuming series expansions and other things. So like they are really like really useful. Like okay, so but like just to continue talking a little bit more. So the idea is that for now, what I'm going to focus in is on these types of infinite sums, what we can say about them. So I'll call them power series. So, and then we'll come back to this issue about like, how is that similar or not to like the function. So like a power series, I'll probably Veritasium or one of those have like a very good video about that. So I'll maybe make you watch one of those so like you see how like like series are used in practice, because it's useful to know their applications. So a power series, the way you should think about it is as some sort of limit of polynomials. That's kind of like the idea. So it's going to be a limit of polynomials. So what I'm going to, the way I'm going to refer to them is as, something like this. Which if you expand out, it would be C0 plus C1x plus C2x squared plus C3x cubed, plus C to the n, x to the n, whatever. So the C's here, you're think of them as kind of like the constants in front, like the terms of x, which in the particular case from before, like they were like this involve like the derivatives divided by the factorial. But this is a little bit more general because like here we're not thinking about like a specific function. So it's like you just take a like a polynomial, the kind of like whatever whatever sequence, of numbers, and you put them in front of powers of x, and you hook it up into like this series. So here C1, C0, C1, C2, C3, C4, is represents like any sequence of numbers. Okay, it's any sequence of numbers. So like the coefficients of like the powers, the coefficients of each term. So for example, your sequence, like just to give you like a concrete example, so that you have like something more like in mind, like the sequence could be the sequence could be one of well, let's say 1 over k plus 1. So because I do want to start them at 0, so in this case, so if the sequence is 1 over k plus 1, then the power series, the way that would look like in this case, one over k plus 1 here times x to the k And what does that give you? At k equals 0, you get 0 plus 1, which is 1. So you get x to the 0. Well, let me put it like this. 1, x to the 0. Then at k equals 1, what do you get? 1 plus 1 is 2. So you get 1/2. And x to the 1 is x. Then what is 2 plus 1? That's 3. So you get 3 x squared, right? Then you get 1/4 x cubed, and hopefully, like you see, like the pattern, right? Like the denominator is 1 unit less higher than the exponent here, like just because of how I chose things. So you can kind of like keep going like that. So like it would be 1/5 x to the 4 plus 1/6 x to the 5, and it goes for eternity, right? So that would keep going forever and ever. So like you would have like 1 over n plus 1 x to the n, and it keeps going, right?
This like approximate any specific function?
I would, okay, for this particular one, I would have to think for a second whether which one it would, because on the top of my head, I don't think this one does agree. At least one that you would recognize immediately. Let me, yeah. So, oh, okay, let's see. So it would be continue to go again. Well, actually, it may. I don't have to know think about it, but yeah, but that's a good question because that's not my point. Now I'm not necessarily starting with the function that I have in mind, right? I don't have that one in mind right now, for example. So this is completely, the coefficients could come from a function with using this derivative formula that I showed you earlier, but they could be totally unrelated to like any function that recognize, right? So that's a useful remark to make. Uh, here we don't have a specific function in mind as of yet, right? So here we are not thinking of a specific function you would recognize as of now. But yeah, eventually we do want to use that. But one of the goals is to but when we do, but when we do have a function in mind, then the idea is that this C case would be like the nth derivatives of the function, divided by k factorial, because like that's like the connection with this Taylor series that I was saying earlier. So no, so yeah, in this particular case, I don't have like a function, so that's not how I found these numbers. I just wrote like some numbers that it's like a sequence that look nice enough, but because the thing is like there are many things you can say about this stuff even before having a function on the back of your head, like of how this works. So the key question whenever you have like an infinite sum of any sort is that finite or not? That's like the main question like ever, So the main question whenever you have so here's like the most important question for anything like this. So I have this formula, right? But I mean, this could be complete nonsense, right? So like the question is, for which values of x can you use that would give you like a finite sum here? That's what I want to ask. So which values of x can you use in the previous formula that give a finite sum? So just to kind of make it even more concrete, if you go back to the function that I had written before, right? Or sorry, to the expression that I wrote before, you know, like where I wrote this thing. What if I try x equals 1? Like just to make this more like clear, like, what if you had tried to plug in x equals 1? So you would write p of 1, right? If you try to plug x equals 1 here, what happens in that case? So you would get something like this. You get 1 to the k, right? So far, so good, everyone with me? So 1 to the k is 1, right? Doesn't matter the higher powers of 1, what they are. And what can you say here? Is that finite or not? You say no, right? So it is basically this 1/n, right? It's kind of like there's almost no difference here. Like it's just like a k plus 1, but like you can do like a comparison with an integral. Like there's so many things that you could try to say why this had to diverge. But if you remember, like the series for 1/n diverges, and basically for the same reason this one would diverge. So like this one would be a infinite number, right? Like so diverges, right? So what that means is that if you were to put x equals 1 here, like this formula makes no sense, or gives you infinity, like depending on how you want to think about it. Um, is that okay? Now, can anyone think of a number for x that you could plug in that would give you something that is finite in this case? And you can go for the lowest hanging fruit of all. So just try to think. Huh? The lowest hanging fruit is if you put 0 here, 0 times whatever is 0. So good, like that, and that's actually and in fact, like at least for now of how I'm writing this formula, this will always kind of work at 0 all the time, right? Because you just get 0 to the k, which is 0. So well, I guess 0 to, I mean, what is 0 to the 0? That's like an annoying question. Like, I don't remember now. That's really fine. But like, it's always finite because like higher powers of 0 would always be. So, but yeah, that's great. Like, so if you put 0, excellent. So you have, all right, 0 to the k. Yeah, and I guess, I think, yeah, 0 to the 0, I think the definition for this is the one is kind of messed up because what is 0 to, I don't remember 0 to, I think 0 to the 0 is just like, the convention is to take it at 0 because 1 to the 0 is 1, right? Or 2 to the 0 is 1. So 0 to the 0 is kind of like trickier, right? Because let's just leave it at 0, but I'll double check on that. But I'm like, except for that one, definitely like, all the others would be 0. So let's just put that at 0, like, yeah, I think that's correct. Yeah, yeah. So like, that's just 0. The important thing is like definitely what's going to be finite because like it's starting at 0, 0 squared, 0 cubed, 0, 4, like all of those are zeros. So like that wouldn't have been issue. But there's even some one that's yeah, so that was why I call that one the lowest hanging fruit. But there's a little one that also if once you have seen this for a while, you can kind of recognize because what if we had put -1? So if you put -1 here, right? What happens if you put -1? You get -1 to the k over k plus 1. And what can you say that this? Why is that? This one is finite, and why is that one finite? Yes. Ready? What's this alternating series test thing? So this is like finite because of like the alternating series. So you see, like this is like these problems are kind of like nice because it's like a nice way to also test knowledge of series from before. Because if you plug in a specific values for x, you are just getting like a good old-fashioned series, right? So as you can see just from this example, kind of like the summary is there are certain values where it doesn't work. For zero, it will always work. I'll write that in a second. And then there are other more like not so clear numbers where you get finite. So like sometimes you get infinity, sometimes you get something finite, sometimes, and then you always get zero at the origin because like of how the power series is structured. So the question is like, how do I know which numbers to plug in? You see? Yes. Oh, because if this was like if you remember we had done like the series for 1/n, and like you could compare this one to like the comparison test with an integral if you wanted. You could compare it with the 1/x, which is like the natural log. With n+1 is essentially the same, but you get x+1 here, but that doesn't change. It's kind of like a p-test for the like a p-series test with p=1. So let me write p-series like with p=1, like just to make it more clear. Is that making sense? Yeah, so but you see, like, so this type of problems, like it's like you can kind of throw at it like a bunch of all different things because you get like a regular series as well. As once you give like specific values. But this is a good example because it really gives you like a sense of what happens. So so like so what this example shows is like shows that there will be values for x for which the series diverges, and there will be other values for x for which the series converges, right? That there will be values. And by converges, I mean that it's finite, right? And diverges, like it's not finite, right? Like it could be because it becomes infinity or because there's just no limit to the series. And other values of x for which the series is diverges. Okay, so in the remaining minutes, I'll give you the one of the biggest things that you need to know about a power series like this, and then I'll just kind of give you like an idea of why it's true. So kind of like the first main result about this stuff is that like, so this is like the first big, like big theorem, you know, like the first important fact about a power series, about so the first important fact is that it will always be finite at zero, which is plausible enough, right? Because if you plug in zero, x equals zero, we already discussed what happens. So the first thing is that at zero, like, and I'll draw it kind of like on the number line. So if you have the number line, x equals zero is good. So here, like this expression makes sense. Like, so what I mean here is that P of zero is finite, right? Um, or convergence. But the cool thing is that the finiteness will extend across an interval. So there will be kind of like a safe zone around zero, which is called the interval of convergence. Okay. So there is an interval center at zero. By center at zero, it just means like the simple like extent, like, you know, zero is the midpoint of that interval. That's why I'm writing it from negative R to R. Where if you choose any number inside that interval, if you choose any number inside this interval, like this series gives you a finite value. Okay. So where if you choose, so like let's say x could be here or it could be here, you know, and x could be anywhere on that interval. P of x will be finite. Okay. Oh, sorry. Yes.
Like how it had before, we're like x equals zero, if it takes a specific one.
Right, like for example, if I it's just like you know, like the thing is like the way the yeah, like I'll write this next time, but like just to answer your question quickly, you know, like later you could center it somewhere else, right? Right, exactly. Yeah, yeah. And then but I always prefer kind of to start at first at zero, but yeah, like and everything else is like just like a shift. So right, if you have done like the power series center at somewhere besides zero, then the interval would be centered at A and it's symmetric about A. Like kind of that's but yeah, I'll definitely write that kind of like precisely next time. But sometimes it's so much it's just easier to understand things with zero first, which is why I like to put everything kind of more concrete there. But of course, then the question, yes.
Oh, like I do all solutions where P of X is finite exists in that interval, or is there just?
No, yeah, oh, right,
Because like in the last one, -1 made it
that's
finite and then.
so that's right, like at the endpoints, like, so that's why I'm writing it at the, as an open interval. At the endpoints, whether it's finite or not, it's not decided by this. But I'm not, yeah, like,
I see.
no, it is, it's always fun when people are interested, you know, so, because it's like a fun question, like, it is really like, that's why I had advertised as the first day of class. I do feel like power series is kind of like just opens itself up for many questions that you want to know the answer to, because like, you know, there are many things that happen once you just start to generalize. So yes, just as a remark, at the endpoints, it's not, from what I'm saying, whether it's finite or not is undecided. Okay, so and then I'll write the formula for R, which is also like obviously something you would like to know. So just to continue this, because at least I do want to give you, before we wrap up, why R comes being the way it is. Yes. Yes, exactly. And when R is infinity, that's where like the convergence kind of goes for the entire number line. And that's kind of like e to the x sine of, you know, like that's where the Taylor series would converge everywhere. That's what we were, yeah, to connect it to what we were saying before. So if the radius of convergence, that is kind of like the best you could ask for, because it's kind of like converges everywhere. Like the formula makes sense everywhere. Yeah.
The negative part and the R, like R is the same variable, I like just.
Right. Like it's just like, yeah, R is called for, before I forget. So there's so many things to say here. So R is called the radius of convergence. Okay. So like just to throw in some terminology, R is called the radius of convergence. So the reason why it's called radius, and actually that may be something I mentioned later at the very end of the course once we talk about complex numbers, is that really like the best way to study this is like if you have imaginary numbers around, because then like you're looking at things on the plane, and on the plane it becomes a disk. So a disk has a radius, and that's where like the name comes from. Like, you know, because on an interval, it doesn't make a lot of sense to call it a radius, but you just have to imagine that there's like a disk hidden in the picture, that when it intersects the x-axis just becomes like an interval. Yeah.
If X is like finite, or does it mean that it matches the function? I didn't know.
Well, that's the thing. Like right now, I'm not thinking about a specific function. If I had chosen, like, if I had chosen, right, you know, if I had chosen like where did I write this? If I had chosen this particular formula for the coefficients, right, then I would mean that it does match like the value of the function there, right? But right now, like this is not coming necessarily for from a function. So it just means like, for example, what I was, where did I have this example? Here you are. But what I mean is kind of what I had here, where like, you know, if you plug in x equals 1, you don't get anything, a finite number, right? But if you plug in x equals -1, you get like a finite number. So I'm saying like there are values of x you can plug in where you get like a number, and there are other values of x you could plug in where the series diverges. That's like what I'm trying to say. But without necessarily having like a picture of like a particular function that you're thinking about, like, you know, we do want to apply this a lot for the case of a function. And in that case, it would mean that it does kind of like give you what the value of the function was at that point. You know, if you had chosen, like, for example, just to make it more concrete, x equals pi, then that would give you cosine of pi. You know, like if you did it for cosine, like when we were talking about earlier about cosine type things of that sort. But for now, it's not coming from like a particular function. Yeah.
Why do we need like a play?
No, it's just and I'm just explaining why it's called radius of convergence, because like the word radius usually refers to a circle, right? But an interval has nothing to do with the circle, but like really, once you add an extra variable, which is called like the complex variable, then all of this becomes a problem of the plane, and then you get like a disk instead of a circle, which has a radius, and that's where like the name comes from.
Oh.
Yeah. So it's just to explain where the name radius comes from, because it's not super obvious. Like when you see an interval, no one says what's the radius of the interval, right? I don't think that's like a common terminology. But like it's called radius of convergence because there's secretly this if you were to, work with complex numbers. So
So is that on like the argument line?
it is on, it's kind of like R2, but kind of like, yeah, I will talk about that towards the end, but yeah, like but yeah, like there are many things, mysterious things that do happen way better. It's like the square root of -1 and this type of thing. So a lot of things just become way better once you have those things around, like so. Okay, but I still, before continuing, what I'm saying is that at the endpoints of this interval, you don't know whether, from what I've said, whether this is finite or not. So before giving you the formula for R, so also at the endpoints, P of -R and P of R could be finite or infinite. Or infinite. So this only works well on the interior of the interval. Okay, you have to kind of like test the endpoints separately. So the endpoints must be analyzed separately. Analyzed separately. So here comes the magic formula for R. How big would this interval be? You can take R. So this is also important. I'll put it in a box. You can take R to be the limit as n goes to infinity of Cn divided by Cn plus 1. And I'll explain where it comes from. It comes from the ratio test. So this is related to the ratio test, actually. So this comes from the ratio test. Secretly, and I'll kind of give like maybe a 2-minute argument for where like, and then we'll stop here. But this is like a magic formula for finding like how big the interval of convergence can be. And again, I'll repeat a lot of that's the disadvantage of Monday, Wednesday classes because between now and Monday, they're like 4 days apart. It's always like a big gap. So I'll kind of repeat some of this stuff next time again, kind of to refresh your memory. But let me just like at least give you like an idea of where this comes from. And that's as I was saying, like this would be the last thing that I write. So why? Because okay, so we were considering, like something that looks like this, right? So call all of this A sub K, AK. So just like a change of, so let's call this AK. So by the ratio test, right? What did the ratio test say? That this sum is finite provided the limit of the ratios was less than 1, right? So if you remember, the ratio test said that if the limit of an plus 1 divided by an plus an is less than 1, right? If you remember the ratio test, 1 is like the key number. So if this ratio had limit strictly less than 1, then the series was finite, right? That making sense? So far so good. Like, okay, let's just work it out for this particular formula for the coefficients. So in this case, what is this limit? This would be the limit as n goes to infinity. What is as an plus one? It would be cn plus one to the x to the n plus one divided by cn divided to x to the n, right? So we would like this to be less than one. That's what we want. So again, this is what we want. We would like. So again, I'll just put it that this is what we want because it's not necessarily true. Like we but this is what we would like. Right? Now we can simplify a little bit this because like what is x to the n plus one? It's x to the n times x, so the x to the n cancel, right? So this is the same as the limit as n goes to infinity of cn plus one divided by cn times the absolute value of x. And again, I would like this to be less than one. Because if I know that this is less than one, then I know that then I would know that the series, that particular sum is finite. Okay, the part again. And then x, this is a limit in n, right? So x does not depend on n, and x is just like a number, so you can take it out of the limit. So again, that's what I would like. And that gives me an inequality that x should satisfy is one over this limit, right? So x should be, so what you would like is for x to be less than one over this limit. And there's this annoying thing of one over a fraction, right? One over a fraction flips everything. So like I'll write it here as a box. Like, if you have one over divided by a divided by b, that's the same as b over a. So like a better way, like this is a little bit too messy. So if you like I'll write it as a limit, but like exchanging the roles. So like what I would like is for this to be less than the limit as n goes to infinity of cn divided by cn plus one, which is precisely what I called r. Yes. Right. Well, I mean, yes, those are okay. So if the limit is zero, right? If like those are extreme cases, I do agree. I mean, there's an assumption that the limit is finite, right. But like like for example, so but those cases like in practice they don't create too much of an issue because like you can kind of tell right away whether that works or not. Like for example, right, if like yes, you're correct. If in order to divide by this, right, I have to assume that this limit is not zero, right? But if it had been zero, then this inequality is always satisfied. It kind of like, you know what I mean? Like, so it is less problematic. I just that is what it looks at first. So it really, think of this as being like a finite number, but there's kind of like fixes that happen in the other two cases because you have to worry even less if this limit is zero. For example, and if this limit had been infinity, then immediately that is never satisfied, unless x equals zero, and that's kind of like a thing. But hopefully I just wanted to give you like an idea of how it's defined, that the way it's defined, and that's where like the R comes from. So that's kind of like, think about it more like, okay, where would you come up ever with this weird looking formula? It comes from the ratio test. But in practice, we'll just use like the formula as it is, and it doesn't cost. You can also, we'll see here whether it gives zero or infinity, and it will kind of like work fine even if dividing wasn't allowed here to me. Okay, I think this is a good place to end. So again, next time, I'll kind of review some of this stuff to, making sure it sticks, and we'll continue talking about these topics. But yeah, let's end here.